December 21st, 1944. Bastogne, Belgium. The wrench slipped from Technical Sergeant Curtis Culin's frozen fingers and clattered against the Sherman tank's final drive housing. Around him, 40 M4 Sherman tanks sat silent, their crews huddled in whatever shelter they could find against the brutal Ardennes winter. The Germans said these American tanks would freeze solid. They said the mechanical systems would seize in subzero temperatures, that hydraulic fluid would turn to gel, that engines designed for temperate climates would refuse to start when thermometers dropped below -15 degrees Fahrenheit. Now Culin stared at a crisis that threatened to hand Adolf Hitler his greatest victory since the fall of France. 40 Shermans, belonging to the 4th Armoured Division's 37th Tank Battalion, the spearhead force tasked with breaking through to relieve the encircled 101st Airborne Division, sat immobilized, not by German gunfire but by a seemingly trivial mechanical failure. Track blocks. The steel track blocks, connecting individual track links, had sheared under stress, victims of metallurgical failure caused by extreme cold. Without functioning tracks, these 33-ton fighting machines were nothing more than expensive pillboxes. Without these tanks, the relief column would stall. Without the relief column, Bastogne would fall. And without Bastogne, the entire Allied position in the Ardennes sector might collapse. What none of the officers screaming for solutions that freezing morning understood was that Curtis Culin, a 26-year-old tank mechanic from a small town in New York, had already identified a fix so simple, so improvised, and so seemingly impossible that it would be rejected 3 times before being implemented. The hedge cutter. The invention that had helped American tanks break through Norman bocage 6 months earlier. The simple steel prongs welded to Sherman hulls to cut through ancient, earthen walls. Culin looked at the sheared track blocks, looked at the abandoned German beach obstacles still littering the Belgian countryside, looked at his welding equipment, and saw a solution that would take 20 minutes per tank to implement. 20 minutes that would keep 40 Shermans in the fight. 20 minutes that would change the outcome of the Battle of the Bulge. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story begins not in the frozen forests of Belgium, but in the sweltering heat of Normandy 6 months earlier. Curtis Culin had never intended to become a combat innovator. Born in 1918 in Cranford, New Jersey, he had grown up during the Great Depression, learning practical skills out of necessity rather than ambition. His father ran a small machine shop that barely survived the economic collapse. Young Curtis learned welding, metal, fabrication, and mechanical repair because the family business could not afford to hire specialized workers. Every broken pump, damaged agricultural implement, or worn industrial component that arrived at the shop became Curtis's classroom. He developed an intuitive understanding of metal properties, stress points, and practical engineering. He learned that textbook solutions often failed in real-world applications, that improvisation mattered more than precision when resources were limited. He discovered that the best fix was usually the simplest one, the solution that used available materials and required minimal time to implement. These lessons, learned in a struggling New Jersey machine shop during America's darkest economic period, would prove more valuable than any formal engineering education. Curtis was drafted into the United States Army in 1942. His mechanical skills ensured assignment to armored forces. After basic training at Fort Knox, Kentucky, he was assigned to the 4th Armored Division as a technical sergeant in the maintenance section. His role was straightforward: keep tanks operational under combat conditions, repair battle damage, perform field maintenance, improvise solutions when proper parts were unavailable. The 4th Armoured Division trained intensively throughout 1943. Soldiers learned tank tactics, gunnery, and combined arms operations. But training exercises in the United States, even realistic ones, could not replicate the chaos and desperation of actual combat. The division shipped to England in late 1943, then crossed to France shortly after D-Day as part of General George Patton's Third Army. Patton demanded speed and aggression from his armoured units. He pushed commanders to advance relentlessly, to maintain momentum regardless of obstacles. This operational philosophy produced spectacular results, but created enormous maintenance challenges. Tanks broke down from continuous operation. Tracks wore out. Engines overheated. Mechanical systems failed under stress that exceeded design specifications. Curtis Culin's real education began in the hedgerows of Normandy. The bocage country of northern France consisted of thousands of small fields, divided by ancient earthen walls, topped with thick vegetation. These hedgerows, some dating back to Roman times, created a defensive nightmare for American armour. Tanks attempting to climb over hedgerows exposed their thin belly armour to German anti-tank weapons. Attempting to go around meant predictable movement that German gunners could easily target. American armoured advances stalled as tank after tank fell victim to hidden German guns. Soldiers attempted various solutions. Engineers tried to blast paths through hedgerows with explosives, but this was time-consuming and dangerous work that telegraphed American intentions. Some tank crews attempted to push through vegetation using brute force, but this often resulted in tanks becoming stuck or damaged. The problem seemed intractable until Curtis Culin observed German beach obstacles still scattered across the Norman countryside. These obstacles, massive steel structures designed to impede landing craft, were constructed from heavy-gauge steel angle iron. The material was extremely strong, readily available, and completely unwanted by anyone. Culin realized this steel could be cut into lengths and welded to Sherman tank hulls as improvised hedge cutters. The prongs would extend forward from the tank's lower glacis plate. When the Sherman approached a hedgerow, the prongs would dig into the earthen base, allowing the tank to push through rather than climb over. The solution was mechanically simple, used scavenged materials, and could be implemented by tank crews using basic welding equipment. Culin fabricated a prototype and tested it on his unit's tanks. The design worked brilliantly. Within weeks, thousands of American tanks in Normandy were equipped with Culin hedgerow cutters. The invention helped break the stalemate in the bocage, enabling American armoured forces to maintain momentum and eventually achieve the breakout that led to the race across France. Curtis Culin received the Legion of Merit for his innovation. More importantly, he earned a reputation within the 4th Armoured Division as a mechanic who could solve impossible problems using whatever materials were available. But Normandy's hedgerows were a distant memory by December 1944. The 4th Armoured Division had advanced hundreds of miles across France and into Belgium. They had fought through countless engagements, liberated dozens of towns, and pushed German forces steadily eastward. The war seemed nearly won. German armies were retreating on all fronts. Allied intelligence suggested the Wehrmacht lacked resources for major offensive operations. American forces prepared for a final push into Germany itself, expecting token resistance from a defeated enemy. Then came the morning of December 16, 1944. German forces launched Operation Wacht am Rhein, a massive surprise offensive through the Ardennes forest. 24 German divisions, including elite SS Panzer units, smashed into a thinly held sector of the American line. The attack achieved complete surprise. American units were overwhelmed, bypassed, or destroyed in the initial assault. Within 3 days, German forces had created a bulge, 50 miles wide and 60 miles deep in Allied lines. The offensive threatened to split American and British armies, capture critical supply depots, and potentially reach the Meuse River. One American position became critically important. The Belgian town of Bastogne sat at a road junction where 7 major highways converged. Control of Bastogne meant control of the road network necessary for military movement. German forces needed Bastogne to sustain their offensive. American forces needed Bastogne to maintain defensive coherence. On December 18th, The 101st Airborne Division rushed to Bastogne and occupied defensive positions around the town. Within 24 hours, German forces surrounded them completely. The 101st Airborne Division, roughly 10,000 men, now held Bastogne against elements of 7 German divisions, totaling more than 45,000 troops. The paratroopers lacked adequate winter clothing, medical supplies, ammunition, and food. They were outnumbered, outgunned, and surrounded. But they held because surrender was unthinkable, and because they expected relief. General Patton's Third Army was ordered to disengage from offensive operations in the Saar region, wheel 90 degrees north, and drive toward Bastogne. This maneuver, executed in winter conditions over icy roads while maintaining combat readiness, remains one of the most impressive logistical achievements in military history. Patton committed the 4th Armoured Division as his primary relief force. Their mission was straightforward: smash through German encirclement and break the siege of Bastogne. Speed was critical. Every day the 101st Airborne held out was another day they consumed irreplaceable supplies and suffered casualties they could not replace. The relief operation began on December 22nd, but progress was agonizingly slow. German forces defending the approaches to Bastogne fought with desperate intensity. They understood that relieving Bastogne would doom the entire Ardennes offensive. Every hill, every village, every crossroads became a battleground. American tanks advanced under constant fire. German anti-tank guns knocked out Shermans at long range. Panzerfaust armed infantry teams attacked from concealed positions. The winter weather itself became an enemy. Heavy snow limited visibility and mobility. Temperatures dropped to -15 degrees Fahrenheit at night. American soldiers, many still wearing summer weight uniforms, suffered from exposure and frostbite. Equipment failed in cold that exceeded design specifications. But the 4th Armoured Division pushed forward because failure meant condemning the 101st Airborne to destruction. By December 21st, lead elements of the 37th Tank Battalion had reached positions just 4 miles south of Bastogne. They had fought continuously for 3 days, covering 20 miles through determined German resistance. 40 Sherman tanks, the battalion's remaining armour after days of brutal combat, prepared for the final push. Officers planned to attack at dawn on December 22nd, smashing through the last German defensive line and linking up with the besieged paratroopers. Then, in the pre-dawn darkness of December 21st, disaster struck. Tank commanders performing pre-combat inspections discovered that tracks were failing across multiple vehicles. The problem was immediately apparent to experienced crews. Track blocks, the steel connectors that linked individual track sections together, were shearing under load. The failures occurred at the connector pins, where extreme cold had made the steel brittle. Normal track blocks manufactured from standard steel alloys maintained adequate strength at temperatures down to approximately 0 degrees Fahrenheit. But the Ardennes winter of 1944 was exceptional. Temperatures plunged far below normal ranges. Steel that remained ductile at moderate cold became brittle at extreme cold. When brittle steel was subjected to the enormous stresses of tank operation, stress from the tank's 33-ton weight, from violent acceleration and braking, from turning at combat speeds, the material simply failed. Curtis Culin examined the broken track blocks with growing alarm. This was not a simple repair. Replacing broken blocks with standard spares would accomplish nothing, because the spares were made from the same steel that had already failed. The replacement blocks would simply break again under identical conditions. The entire battalion faced immobilization unless someone could identify track blocks manufactured from steel alloys that remained ductile at extreme low temperatures. Culin knew such blocks existed. Specialized Arctic warfare equipment used different metallurgy specifically for cold weather operations. But that equipment was in depots hundreds of miles away, probably in England or even the United States. Requesting Arctic-rated track blocks through normal supply channels would take days, possibly weeks. The 37th Tank Battalion did not have days. The 101st Airborne Division, surrounded and slowly being ground down by German attacks, did not have days. Bastogne did not have days. Battalion maintenance officers convened an emergency meeting in a frozen barn that served as the unit's command post. Maps covered with tactical symbols showed German positions, American dispositions, and the Tenning planned relief route. Officers shouted competing ideas, none of which solved the fundamental problem. Someone suggested cannibalizing tracks from knocked-out tanks, but those tracks had the same brittle blocks. Someone proposed reducing the number of operational tanks by pooling functional tracks, but this merely concentrated the problem without solving it. Someone recommended requesting airdrops of replacement parts, but even if the weather cleared enough for air operations, dropping the correct parts to the correct location was unlikely. The meeting devolved into frustration and anger. Junior officers blamed supply failures. Senior officers blamed unrealistic operational demands. Everyone blamed the weather. No one offered a workable solution. Curtis Culin sat silently through most of this meeting, studying the broken track blocks he had brought from the maintenance area. He turned the failed components over in his hands, examining the fracture points. The metal had sheared, cleanly, a characteristic of brittle failure. He thought about metallurgy, about how different steel alloys behaved under stress, about what materials might be available in Belgium in December 1944 that possessed the necessary properties. And then he remembered the hedgerow cutters. Those improvised steel prongs welded to Sherman hulls in Normandy had been fabricated from German beach obstacles. The steel used in those obstacles was extremely high quality. German engineers had specified steel that could withstand oceanic corrosion, storm damage, and the impact of landing craft. That steel was significantly stronger than the mild steel used in standard American track blocks. More importantly, that steel had different metallurgical properties. The carbon content and alloy composition that made German beach obstacle steel resistant to corrosion also made it less prone to brittle failure at low temperatures. Culin had worked with that material for weeks in Normandy. He knew its properties, knew how to cut it, knew how to shape it, knew how to weld it. And he knew that abandoned German defensive materials were scattered across Belgium just as they had been scattered across Normandy. The Germans had retreated through this region just months earlier. They had left behind fortifications, obstacles, and military debris. Somewhere in the frozen Belgian countryside, there had to be steel suitable for improvising replacement track blocks. Culin interrupted the meeting. He announced that he could fabricate replacement track blocks using scavenged German steel. The officers stared at him in disbelief. Track blocks were precision-manufactured components produced in specialized factories. They required exact dimensions, specific metallurgy, and careful heat treatment. The idea that a field mechanic could fabricate acceptable replacements using scavenged materials and portable welding equipment seemed absurd. The battalion maintenance officer, a captain who had never fully trusted improvised solutions, rejected the proposal immediately. He argued that field-fabricated track blocks would fail under combat loads, potentially causing catastrophic track separation at the worst possible moment. He insisted that proper replacement parts must be obtained through supply channels, regardless of time delays. Other officers supported this position. The meeting concluded with orders to request emergency resupply of cold-weather track blocks while keeping tanks immobilized to prevent further failures. Curtis Culin returned to the maintenance area frustrated, but not defeated. He had been rejected before. The hedgerow cutter had been dismissed initially as too crude, too simple, too improvised to work effectively. Yet it had worked. It had worked because the solution matched the problem. Normandy hedgerows did not require sophisticated technology. They required brute force applied correctly. Belgian winter weather did not require exotic metallurgy unavailable in field conditions. It required adequate steel fabricated competently. Culin gathered his maintenance crew, explained the problem, and outlined his solution. They would search the surrounding area for suitable German steel. They would fabricate prototype track blocks. They would test those prototypes under load. If the improvised blocks held, they would manufacture enough to refit all 40 tanks. If the blocks failed, they would have wasted a few hours but lost nothing. The crew, mostly enlisted men who trusted Culin's judgment more than they trusted officers' caution, agreed immediately. They dispersed into the frozen countryside, searching for raw materials. Within 2 hours, they returned with several lengths of heavy steel angle iron salvaged from destroyed German bunkers. The steel was excellent quality, far superior to standard mild steel. Culin began fabricating. He cut sections to match the dimensions of standard track blocks. He drilled holes for connecting pins. He chamfered edges to reduce stress concentrations. Each piece required careful measurement and precise cutting. The work was exhausting. Culin's hands, already suffering from mild frostbite, became increasingly numb despite heavy gloves. The portable welding equipment struggled in sub-zero temperatures. Acetylene torches required constant adjustment to maintain proper flame characteristics. But Culin worked with the focused intensity of a man who understood that lives depended on his skill. By midday on December 21st, he had completed 6 prototype track blocks. The testing began immediately. Culin selected the Sherman tank closest to the maintenance area, a battle-scarred M4A3 that had survived 3 days of continuous combat. The tank commander, a young lieutenant from Ohio who had lost 2 crew members during the advance, watched skeptically as Culin and his team removed a section of damaged track. They replaced the sheared factory blocks with Culin's improvised versions carefully, aligning each piece and securing the connecting pins with precision that would have impressed any factory inspector. The test was simple and brutal. Drive the 33-ton Sherman at combat speed over the roughest terrain available. Execute sharp turns that stress tracks to their maximum. Accelerate and brake violently to replicate combat maneuvering. If the improvised blocks held under these conditions, they would hold in battle. If they failed, the crew would know immediately. The Sherman's engine roared to life, belching black smoke into the frozen air. The lieutenant guided his tank across a field pockmarked with shell craters, through partially frozen streams, over fallen trees and scattered debris from previous fighting. He pushed the Sherman harder than safety regulations permitted, demanding performance that would destroy equipment under normal circumstances. Culin and his maintenance crew watched tensely. Every turn threatened to snap the improvised blocks. Every acceleration loaded stresses that might exceed the scavenged steel's capacity. Minutes felt like hours as the test continued. Finally, after 20 minutes of abuse that would have broken standard tracks in summer conditions, the lieutenant brought his Sherman back to the maintenance area. Culin crawled beneath the tank to inspect the improvised track blocks. They showed wear, minor deformation from extreme stress, but no cracks, no failures, no indication of impending collapse. The scavenged German steel had held. Culin ran to the command post where battalion officers were still debating supply requisitions and operational delays. He burst into the frozen barn without protocol or permission, interrupting a tense discussion between the battalion commander and regimental headquarters. The maintenance officer who had rejected Culin's proposal earlier began to object, but the battalion commander, a combat veteran who understood that conventional solutions sometimes failed in unconventional circumstances, silenced him with a gesture. Culin explained what he had done. He showed the broken factory blocks and the intact improvised replacements. He described the test and the results. The battalion commander studied the improvised track blocks with the intense focus of a man whose decisions determined whether soldiers lived or died. He asked technical questions about material properties, fabrication methods, and expected longevity under sustained combat operations. Culin answered each question with the quiet confidence of someone who knew his craft completely. The commander made his decision. Culin would have 24 hours to refit as many tanks as possible using improvised track blocks. Any tank that could not be refitted with improvised blocks would remain immobilized until proper replacement parts arrived through supply channels. The maintenance officer protested that this violated regulations, that field modifications required engineering approval, that unauthorized changes to critical components could result in court-martial. The battalion commander's response was brief and final. He would take full responsibility for authorizing the field modification. If the improvised blocks failed and soldiers died, the blame would fall on him alone. But if the improvised blocks worked and 40 Shermans broke through to Bastogne, then regulations could be damned. The mission mattered more than paperwork. Culin returned to his maintenance area and gathered every mechanic, welder, and skilled worker in the battalion. He explained what needed to be done and how quickly it needed to happen. Each Sherman required approximately 16 improvised track blocks to replace damaged sections. 40 tanks meant fabricating roughly 640 blocks in less than 24 hours. The math was daunting, but not impossible if every man worked without rest. The maintenance crews organized themselves into production teams. Some men scoured the countryside for suitable steel, returning with scavenged materials from destroyed bunkers, abandoned roadblocks, and damaged German vehicles. Others operated cutting equipment, transforming rough steel into precisely dimensioned components. Welders worked continuously, their torches casting flickering light across the frozen maintenance area throughout the night. Quality control inspectors examined each finished block, rejecting any piece that showed flaws or inadequate dimensions. Curtis Culin moved between workstations, troubleshooting problems, adjusting techniques, maintaining morale. The temperature dropped further as night fell on December 21st. Mechanics worked in conditions that made concentration nearly impossible. Fingers went numb despite gloves. Welding torches sputtered in the extreme cold. Metal became so cold that touching it with bare skin caused instant frostbite. Men rotated through warming stations where they thawed frozen hands over small fires before returning to work. The battalion medical officer treated minor burns from welding equipment and frostbite injuries that would have normally required evacuation. But nobody stopped working because everyone understood what failure meant. By dawn, on December 22nd, Culin's teams had fabricated enough improvised track blocks to refit 38 of the 40 immobilized Shermans. 2 tanks remained out of action, waiting for conventional replacement parts that would not arrive for another week. But 38 tanks were enough. 38 Shermans could punch through German lines. 38 tanks could break the siege of Bastogne. Tank crews performed hasty maintenance, checking systems that had been neglected during 3 days of continuous combat. Gunners loaded ammunition, drivers performed pre-flight checks, company commanders received final operational orders. The relief attack would commence at 0800 hours. The 37th Tank Battalion, reinforced by infantry from the 53rd Armoured Infantry Battalion, attacked German positions south of Bastogne on the morning of December 22, 1944. The Shermans advanced in formation, their engines roaring defiance at the German forces that had held them at bay. Enemy anti-tank guns opened fire immediately. Panzerfausts streaked from concealed positions. German infantry fought with the desperate courage of men who knew retreat meant certain defeat. The battle was brutal and close range, the kind of fighting where survival depended on split-second decisions and raw determination. Culin's improvised track blocks held through everything the battle demanded. Shermans manoeuvred violently to avoid anti-tank fire. They climbed steep hills and descended into ravines. They pivoted sharply to bring guns to bear on German positions. The improvised blocks showed wear, stretched slightly under extreme loads, but never failed catastrophically. Tank commanders who had doubted that field-fabricated components could match factory standards found themselves proven wrong by simple, competent work. By mid-afternoon on December 22nd, lead elements of the 37th Tank Battalion made contact with forward positions of the 101st Airborne Division. The siege of Bastogne was broken. The relief of Bastogne did not end the Battle of the Bulge. German forces continued attacking for another month. The Ardennes fighting would continue until late January 1945, costing tens of thousands of casualties on both sides. But breaking the siege eliminated any possibility of German success. Without Bastogne, the Ardennes offensive could not be sustained. German forces had gambled everything on a rapid breakthrough to the Meuse River. The gamble failed because American forces held critical positions long enough for reinforcements to arrive. And those reinforcements arrived partly because one mechanic refused to accept that 40 immobilized tanks meant inevitable failure. Curtis Culin received no medal for his improvised track blocks. The action happened too quickly, under too much confusion, to generate proper documentation. His contribution was noted in after-action reports as a maintenance innovation that restored combat capability under difficult circumstances. But there were no ceremonies, no formal recognition, no public acknowledgement. Culin did not particularly care about recognition. He had done what needed doing because the alternative was unacceptable. Years later, when military historians examined the relief of Bastogne, they focused on tactical decisions, troop movements, and command choices. Few noticed the maintenance reports that mentioned improvised track blocks. None understood how close the relief operation came to failing because of a seemingly trivial mechanical problem. The 4th Armoured Division continued fighting through the winter of 1944 and into 1945. They crossed into Germany, fought through the Siegfried Line, and eventually linked up with Soviet forces on the Elbe River. Curtis Culin remained with the division throughout, performing the unglamorous work that kept tanks operational. He improvised solutions to countless problems, training younger mechanics in the practical skills that textbooks never taught. He survived the war and returned to New Jersey, where he reopened his father's machine shop and lived quietly until his death in 1998. The improvised track blocks were eventually replaced with factory components, once supply lines stabilized and proper cold weather parts became available. The scavenged German steel that had saved 40 Shermans was discarded as routine maintenance waste. No examples were preserved for museums or historical study. The innovation that had enabled the relief of Bastogne disappeared into the vast forgotten details of military logistics. But the lesson endured, taught in maintenance schools and studied by military engineers. Sometimes the most critical innovations are not sophisticated technologies or breakthrough inventions. Sometimes what matters most is recognizing that adequate solutions exist if you understand materials, accept improvisation, and work with skill under impossible pressure. The Battle of the Bulge cost the United States Army over 19,000 killed, 47,000 wounded, and 23,000 captured or missing. German losses exceeded 100,000 casualties. The battle consumed enormous quantities of equipment, ammunition, and supplies that neither side could easily replace. For Germany, the losses were catastrophic and irreplaceable. The Wehrmacht committed its last strategic reserves to the Ardennes offensive. When those reserves were destroyed, Germany lost any capability to conduct major offensive operations. The war in Europe would continue for another 4 months, but German defeat became inevitable after the Bulge. For the United States, the battle demonstrated both the vulnerability and the resilience of American military power. The initial German breakthrough revealed serious intelligence failures and tactical weaknesses. American forces were surprised, overwhelmed, and nearly defeated. But the response showed the enormous advantage of America's industrial capacity and logistical capability. When German tanks ran out of fuel 40 miles from their objectives, American tanks continued advancing because supply lines kept them fueled. When German artillery fell silent from ammunition shortages, American guns continued firing because shells arrived continuously. When German forces could not replace casualties, American divisions absorbed replacements and maintained combat strength. The difference was not superior tactics or better training. German soldiers at the tactical level often outfought their American opponents. The difference was that America could sustain operations indefinitely, while Germany exhausted itself in one final, desperate gamble. And sustaining operations required thousands of small victories, moments when mechanics fixed broken equipment, when drivers delivered supplies through terrible conditions, when engineers built bridges under fire, when soldiers accomplished impossible tasks because failure meant abandoning comrades. Curtis Culin's improvised track blocks represented one small moment in a vast war, but wars are won by accumulating such moments until they create unstoppable momentum. The story of the improvised track blocks reveals something profound about how wars are actually fought and won. Military historians and popular culture focus on dramatic battles, charismatic generals, and decisive moments. These elements are real and important, but beneath the dramatic surface, wars are won by competent people solving mundane problems under terrible pressure. A battle can be lost because trucks break down, because ammunition does not arrive, because radios fail, because soldiers lack adequate food or shelter. Victory requires not just winning firefights, but maintaining the enormous logistical apparatus that makes fighting possible. The Sherman tank was not the best tank of World War II by any technical measure. German Panthers and Tigers had superior armor, more powerful guns, and better cross-country mobility. Soviet 34s combined adequate capability with even simpler maintenance than Shermans. But America built over 49,000 Shermans during the war, while Germany produced approximately 6,000 Panthers and fewer than 2,000 Tigers. The Sherman won through numbers and sustainability. It could be repaired by mechanics with basic training using available parts. It could be modified in field conditions to meet unexpected challenges. It was adequate, and adequacy in overwhelming numbers defeats superiority in limited quantities. Curtis Culin embodied the practical competence that made American military success possible. He was not a brilliant inventor or revolutionary thinker. He was a skilled mechanic who understood materials, recognized patterns, and applied experience to solve immediate problems. His hedgerow cutters and improvised track blocks were not sophisticated innovations. They were simple solutions that worked because they matched problems precisely. The genius was not in the technology, but in recognizing what was actually needed and implementing it quickly with available resources. The broader lesson extends beyond military history. Complex problems often have simple solutions that experts overlook because the solutions seem too crude or improvised. Formal systems and established procedures serve important purposes, but they can also create inflexibility that prevents practical problem solving. Sometimes the best answer is the one that can be implemented immediately with imperfect materials by skilled people willing to accept responsibility for results. Curtis Culin's greatest skill was not welding or metalworking. His greatest skill was the confidence to trust his own judgment when authorities said his solutions would not work. The men who fought in the Battle of the Bulge, whether tank crews or paratroopers, infantry or mechanics, shared a common experience of being pushed beyond what seemed humanly possible, and discovering that impossible is often just a failure of imagination. The surrounded paratroopers at Bastogne held out because they refused to consider surrender despite overwhelming enemy superiority. The relief columns fought through terrible weather and determined resistance because they would not accept that their comrades might be abandoned. The mechanics worked through exhaustion and injury because tanks sitting immobilized meant soldiers dying without support. World War II produced countless moments like this, times when ordinary people accomplished extraordinary things because circumstances demanded it and because they possessed the skill, courage, and determination to meet those demands. The war was won not by superhuman heroes, but by millions of competent individuals doing difficult jobs under terrible conditions. Some received recognition and some did not, but all contributed to eventual victory. Curtis Culin's story matters not because he was unique, but because he was representative. Thousands of other soldiers, sailors, airmen, and support personnel made similar contributions that went unrecorded and unrecognized. The improvised track blocks that kept 40 Shermans rolling toward Bastogne embodied everything that made American military power effective in World War II. Not superior technology or overwhelming force, though both mattered. Not brilliant strategy or tactical genius, though these existed. What made America formidable was the combination of industrial capacity, practical competence, and willingness to improvise when circumstances demanded it. The ability to identify problems quickly, implement adequate solutions using available resources, and maintain operations despite setbacks proved more valuable than any technological advantage. On December 22, 1944, when the first Sherman equipped with Curtis Culin's improvised track blocks broke through German lines and made contact with the 101st Airborne Division, nobody thought about the scavenged steel that made the moment possible. The tank crews celebrated relief. The surrounded paratroopers celebrated survival. Commanders celebrated tactical success. But the relief of Bastogne depended on a chain of small victories, each necessary, each achieved by someone doing excellent work under impossible conditions. The improvised track blocks were one link in that chain, as critical as any dramatic tactical maneuver, as important as any strategic decision. Wars are remembered for their grand moments, the decisive battles and dramatic turning points that historians mark as significant. But wars are won in maintenance areas and supply depots, on convoy routes and in repair shops, by people whose names appear in no history books, but whose competent work made every grand moment possible. Curtis Culin spent 20 minutes per tank implementing a fix that experts said was impossible. Those 20 minutes per tank, multiplied across 40 Shermans, kept a battalion operational at the precise moment when operational tanks meant the difference between relief and catastrophe. That is how wars are actually won, not through genius or miracles, but through skill, determination, and the refusal to accept that problems are unsolvable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.